Alright, so we're going to start looking at the graphs of these things, and so we're going to start here looking at a t-table, and we're doing f of x equals 2x and comparing it to log 2 of x, so we can see the same thing here. Alright, so if we start here with just plugging in 2 to the x, if we plug in 0 we get 1, if we plug in 1 we get 2, 2 we get 4, 3 we get 8, and then we can go back to the negative ones. It's just going to be the inverse of the positive. So 2 to the negative 1 is 1 over 2. Flip it over. And so if we were to graph this like we did in 3.1, very first important point here is 0, 1, and we would also have 1, 2, and we don't need to plot all the points because we know the general shape is going to look like this. Alright, so what's going to happen with our logarithm function? Well, the logarithm function is just the inverse of exponential. So what does that mean? That means flip the x's and the y's. So if we take the t-table here for 2 to the x, the t-table for log 2 to the x is just going to be the exact same thing flipped over. So 1/4, we get 2. 1/2, we get, negative 2, negative 1. 1, we get 0. 2 and 1. 4 and 2. 8 and 3. And so if we were to go ahead and graph this, the important point here is no longer at 0, 1, it's at 1, 0. And that's going to be a point that every parent log function is going to have, because every time that you raise a power to the 0, you get 1. So it's flipped over. And as we go through this, the graph is going to be the inverse. It's going to look like that. All right, the flip of the exponential functions. Okay? All right, so one thing to notice on here for the logarithms is we will have a vertical asymptote that we can't quite get to, and so that's going to come into play on some of our graphs later on. All right, and so there's a nicer drawn graph in the book showing you the difference between the exponential and the logarithmic functions. All right, so we can sketch the graph of a log function with a calculator or without a calculator. You'll notice some nice pretty values in there. We can go ahead and take a look at our calculator, and the one thing to keep in mind on here is here's our important point on a parent function if we're not shifting. This is 1, 0. And really you just need to find one more point, because we know our asymptote is going to come over here at the y-axis, and if so we could find one more point, we can draw this nice smooth curve and sketch it out. All right, the graphing calculator is going to be more precise, but we can come up with a nice sketch on our own. All right, so let's talk about shifting graphs, and then we'll try one on our own. Works exactly the same way. We'll look at log of x minus 1. All right, what's going on here? We're shifting this graph 1 to the right. So our important point used to be 1, 0. Now it's going to be 2, 0. Our asymptote used to be the y-axis, and now it's going to be shifted over by 1. And so this graph will come down and will never cross x equals 1. Alright, so we're just moved over. Follows the exact same rules of everything we've done before. So if we look at the second example, the 2 here, it means we're going to shift everything up by 2. So let's see if you can do this. This is a matching problem. So 45 is going to match with one of the graphs on the left, A, B, C, D, E, or F. Take a minute, see if you can match this up. Alright, the correct answer on this is C. And the reason why is we should be crossing through this point right here, but since it's that plus 2 on the end, that means we're shifting up 2. And so now we're crossing through, instead of 1, 0, we're going to be crossing through 1, 2 as our important point. The asymptote doesn't shift, so we still want to be here. And so this is the only graph that fits those two requirements.